So my goal is to start undoing other rules. We undid the chain rule with substitution. There are a lot of specific applications that use substitution in particular ways, but there are lots of other rules. So let's pick one of those. We can undo sums and differences. Those are direct. Constants and constant multiples. Chain rule. Look at the third one we did, the product rule. Products and quotients. So let me think for a second about the product rule. When you take the derivative of a product, what do you do? Derivative of the second times the first, or the first times second, add them together. I've left off the of x part, but it's implied. Let me take this same rule and write it with antiderivatives in it. So if I have this idea, the antiderivative of that is fg. But that means that fg is the antiderivative of this. And those are integrals dx. I start thinking about substitutions again. If we were going to do a substitution, I'd say u equals some part of this, right? Some part of this over here would be a u. And then I'd take the derivative of that. So what if I said, well, u is going to be our f of x? Well, what's du? Now here's the sneaky part. All the stuff we did yesterday, u and du are in the same place. F prime is over here. F is over here. They're not in the same place. That's not good. How can I fix that? And I have done nothing about g at all here, have I? Let's try a second parallel substitution. At the same time that we're making that u, let's do another substitution to go with it. Call that v. What's dv then? G prime of x dx. All right. I'm going to take that exact equation that we've written there in f's and g's and write it in u's and v's. This left side is uv. And then over here, I have two integrals. I have u and dv. And over here, I have v and du. Oh. So in one sense, trying to work the product rule backwards makes me have to have that right side rigged properly. I have to be able to see two different pieces matched up like this. Or I could look at an integral and say the two pieces I see in this integral are not related to each other, and then treat them like one of these pairs. Either that's a u and a dv, or it's a v and a du. How do I get the other stuff? I can rearrange this equation. Now, all I've done is I subtracted this v du over to the other side, and then I switched the two sides so that I'd have the integral on one, and I write it in an integral on the other. So it's uv minus the integral of v du. A number of years ago, when you hear uv, what do you think? Ultraviolet, right? Okay, ultraviolet voodoo, VDU. It's a nice and easy mnemonic to stick that in your head. To do integration by parts, it's ultraviolet voodoo. I promise this isn't black magic, but we're getting close. What the is this really about? Let's look at an integral that I have no way of identifying how to do with any substitution. There's nothing connecting the exponential e to the x with that x outside. If I tried to say, well, that's an outside and an inside, but the inside would only be x. If I changed that, I'd end up just changing all the letters, and that wouldn't do me any good at all. So I'm going to say this is really a product of things, an x and an e to the x, and that product cues me in. I should look at the product rule. So I say to myself, what could I do to decide on u and dv to match the left-hand side here to this, and then what will I get over here? Well, that means you have two choices. You could say, all right, well, I'm going to take the u to be the x, I'm going to take the u to be the e to the x. Flip a coin, which one do you want to do?
U equal x.
Okay, hold that thought. If I make u equal to x, then I'm going to need du. Over here, I'm going to have v and dv. If the u is the x, then everything else in that integral, including the differential, must be dv. Those are my two parts then, u, dv. Well, what's the derivative of x?
1.
So my differential is just dx. But now over here, I need to go the other way. What's the antiderivative of e to the x? Just e to the x. And now I say, if I mix and match to do the right-hand side with these four parts, what do you get over here? Well, I get uv minus another integral. What's the new integral? Well, that's the voodoo part. That's v du. V du. Here's the best part about the choices we made. That integral on the right is easy. I know how to do that. Integration by parts is a type of a larger category of formulas. It's a reduction formula. It took an integral that was complicated and reduced it to an integral that was easier. And that's my goal in my choices for U and V, is to figure out what's reducing my formula here. I could have chosen the other way. If I had done the other choice, then what would I get for V and du? Yeah.
It would be 1/2 x squared. It would be e to the x dx.
And notice now, this is still correct to write that the integral of x e to the x dx is uv minus the integral of v du. But this integral at the end here on the right is harder. I don't know how to do that one. I didn't reduce my formula. I made it more complicated. This is a bad sign. Wah. So my goal is to choose carefully, to figure out what should be my u and what should be my dv, what should be which part. Once I've made the choice, I just churn through that product rule formula backwards. My uv minus v du, and I run and see if I get something that works better. Questions? Thank you. How do I know what to pick? Yes, there is a mnemonic, a method that allows me to say I'm probably best off choosing this or this or this or this to be u versus dv. I'm going to list these in the first thing I see going down this list is probably the thing I want to make u. So I'm going to go LIPET. If I see something that is logarithm, I think that should be u. If I don't see a logarithm, but I see an inverse trig, then that should be u. If I don't see either of those, but I see a polynomial, that should be u. If I don't see any of those, but I see an exponential, that should be u. And last but by no means least, if the only thing I see is trig stuff, that's going to be my choice of u. Now, this particular method for choosing is fairly recent. This acronym LIPET didn't actually show up in textbooks until the late 90s, early 2000s. So I didn't learn it in school. I just guessed. And literally, I would ask, am I reducing things? In that case, my idea of reduction meant making either things smaller in power or smaller in the number of terms. That's why I don't like picking u to be trig, because what happens if you get a secant, you take a derivative, you get secant times tangent. You take a tangent, you take a derivative, you get secant squared, I get more stuff. So instead of reducing, I'm expanding, and that hurts. Inverse trigs. I can make inverse trigs turn into functions of x, because the derivative of inverse tangent is 1 over 1 plus x squared. The inverse sine is 1 over the square root of 1 minus x squared. So all of a sudden I get things that are in x that aren't trig, inverse trig. Logarithms, their derivatives become powers of x. I like that. They make reduction easier. But now that I have this, I'm going to abuse the hell out of this. And that means that the choice you made, Leo, is exactly backed up by this. Because my two choices were x or e to the x. Polynomial comes before exponential. I should pick the x to be my u term, and that's what we did. More questions? Or examples? What are my two pieces?
X and cosine of x dx.
Because x is a polynomial, cosine is trig. Polynomial comes before trig in my list. U should be the x. There we go. You don't have to lay this out the way I do, but just like I said, I'm reducing versus increasing. I always think of derivatives somehow as going down. It comes from the power rule, right? Powers kept going down. So I think of taking a derivative as going down. And thus taking an antiderivative is going up. And that's why I write u and dv, and then v is above and du is below. I don't care how you lay it out. Feel free to lay it out any way you want. But that lowering power, raising power thing is what's been stuck in my head for way longer than I care to admit. So the derivative of x is 1 dx. The antiderivative of cosine of x dx is? Be careful. Minus sine is the derivative of cosine. Derivative of sine is just cosine, so the antiderivative of cosine is just sine of x. And I don't need the plus c, because I'm not going to do the plus c until after I've done that second integral. So I don't need the plus c in here. Okay, that means this integral is equal to uv minus the integral v du. Please notice if I put the plus c in here, when I integrate, I'll get a number times x, right? But that could also be incorporated into the change I made by doing it here. So I don't need it until the very end. Because this is still an integral, I don't actually need to incorporate that plus c until I've finished integrating. In this case, what's the integral of sine of x? Which changes this sign. And there we go. How do you know if you got it right? Work backwards. Sometimes parts are hiding. Just like our u substitutions were hiding yesterday, right? When we did tangent, we had to rewrite it as sine and cosine. And my first reaction is, I only see one part. How can I do integration by parts if there's only one part to begin with? Everything, every algebraic expression you have has a 1 in front of it. So if I think of this logarithm as ln of x times 1, I really do have a second part. All right, let's try that. If I think of that as being ln of x times 1, 1 is a constant's a polynomial. It's x to the 0th power. That means I have a logarithm in a polynomial, which should be u. A logarithm. I don't even have to write the 1. I could just write dv equals dx. But then v and du. Du is? Yeah.
1 over x dx.
And v is just x. Yeah. Okay. Ultraviolet voodoo time. Write out the other side for me. This integral is equal to uv. Because of the ln of x, I tend to write other stuff in front of that. So I'm going to write x ln of x rather than ln of x times x minus the integral of v du, x times 1 over x dx. And what wonderful thing happens to me? Do the multiplying. What's x times 1 over x? 1. That, oh, you sneaky person, you give me an integral that is easier on the other side. Unfortunately, Maddie, you're not wrong. We may run into situations where we do our integration by parts, and then the next integral we get needs it again. As a matter of fact, the integral we did to begin with, x e to the x, right? I'm going to change that just the barest bit. Square that. So instead of x e to the x, I have x squared e to the x. What happens now? I'm going to do exactly the same integration by parts setup we did before. I have a polynomial and an exponential. Polynomial is first in my list before exponentials. That's my u. But that means du is 2x dx, and v is e to the x. So when I apply the integration by parts formula, that second integral, if I take the 2 out in front, is x e to the x again, isn't it? Fortunately, I know what to do. And it's not impossible, it's just tedious. I get to do it again. Now, I saw online somebody write a column where they kept taking derivatives over and over and over, and a column where they kept taking integrals over and over, and they would move back and forth diagonally between the two to do repeated integration by parts. My problem is that I don't know how they knew in advance they were going to need to do repeated integration by parts. And so I don't prefer that method unless, I recognize, oh, this is going to be a problem that needs integration by parts 4 times. How are you supposed to recognize it? I've seen a million of these. You've seen 5. So I actually prefer to say, oh, I still need parts. Let's go again. So now that I know I need parts again, I even know what those parts are. X and e to the x dx, because that's what we used the first time. E to the x dx. But now the uv minus v du is all multiplied by that 2 that's out front. uv minus the integral v du What happened, Maddie? Yeah, got to keep all the pieces, yes. So now I have x squared e to the x minus 2 quantity, x e to the x minus e to the x plus c. I am the kind of person who will take that negative 2 and multiply it through. X squared e to the x minus 2x e to the x plus 2e to the x. And 2 times a constant is still a constant. You could change it if you wanted to. You could write 2c, you could write capital D, whatever. It's still a constant. I did find the answer in the back of the textbook I got this problem from. Did one more algebraic simplification. They factored out e to the x. I think that's, a little above and beyond and not really required. I will say that if you see a power of x with an exponential, you will need integration by parts for as many times as the highest power of x you see. So if I had x to the 4th e to the x, I'd have to do integration by parts 4 times. If I had x to the 7th e to the x, I'd be doing integration by parts 7 times. I think I'd rather hit myself over the head with a 2x4. But we could do it. I just don't think it's worthwhile. Questions? Usually at this point, somebody says to me, well, you've undone product rule, can you undo quotient rule? And the answer to that is, most of the time, it's way more energy than it's worth. This past spring, I went to the Math Association of America conference in West Virginia. And a student from the University of Pittsburgh asked that question and answered it. And in the very first edition, the very first issue of the University of Pittsburgh's undergraduate math research journal, there's an article called The Inverse Quotient Rule. It only applies in a very small handful of cases. Almost all the time, it's better to take your inverse quotient and write it as a product, 1 over something times something, like we did with our tangent yesterday. So there is one, and I will happily share with you the link to the paper. I believe it's on our Canvas paper. If I forgot to put it up, it'll be there later today. But I'm much happier saying, no, we should really just deal with products. Inverse quotient is very unpleasant. Questions? Maddie?
So, in the top part, where you factor out the 2. When you get it to the point where it's -2, yeah, you're good. So when you take the second integral and do it again, keep that as x to the x if you don't integrate that.
Ah, because here, that's our UV.
Okay. Okay.
That's the sneaky part of that one. Because that's what we did back here. Now, there are some cases where we kind of get trapped in a loop. According to my mnemonic, what should I make my choice of u here? The exponential. Exponentials come before trig. So I'm going to let u equal e to the x and dv equals sine x dx. What's du? Yeah. E to the x again. Derivative of e to the x is e to the x. And the antiderivative sign is? That's where the minus shows up. Minus cosine x. So uv minus the integral of v du. Minus a minus is a plus. So I end up with minus e to the x cosine x plus, oh look, what do I need to do with that other integral?
Integrate again my part.
Crap. Okay. So now, what's my choice of u? It's e to the x again. And that means that dv is cosine of x dx, and that means that v is sine of x. And now I see a problem. Because when I write up my next version, uv minus the integral v du what just happened? Say it louder, Maddie. We're back where we started. But here's something very interesting. This exactly matches that, doesn't it? No. It means that I had to get all the way to here to get my answer. But this one over here is negative. So what if we moved it to that side of the equation? Remember, this thing is still on the left here, isn't it? Over here on the left, I still have the integral e to the x sine x dx. So I have thing, and then I have minus that thing over there. Let's put them both on the same side. I get twice the integral. E to the x sine x dx is equal to minus e to the x cosine x plus e to the x sine x, which means all I have to do is divide by 2. The fact that it was exactly the same as where I started, Maddie, is the reason I was actually happy to see this again. I got back the exact same thing, and I could combine my like terms. But then I'd have equals 0, right? And I would have solved my problem. What is this thing equal to? Now I have exactly what you wanted this integral. I know what this integral is. The one thing that's missing from this whole problem is, yeah, got to be in there somewhere. This is a rare case. Now, again, I will freely admit this sort of looping process, because I see a second integration by parts or a further integration by parts, is mostly going to occur when things don't reduce. Sine and cosine keep going in circles. Your sine is cosine, your cosine is minus sine, minus cosine, sine, cosine, minus sine, minus cosine. It goes around and around and never gets anywhere. So that's the reason this one circles back on itself. Secants and tangents won't do that. Cosecants, cotangents won't do that. The inverse trig functions won't do that. It turns out that this exact integral and several others very much related to it show up in physics, chemistry, biology and biochemistry, ecology. I'd love to tell you you're never going to see this crap again. Medicine, neural feedback, molecular, intramuscular chemistry is all in here. I'd love to tell you this never comes back up. I see this everywhere. Matter of fact, the one I like the most is an e to the x sine x. It's e to the minus x sine x. What's different about e to the x versus e to the minus x?
Y is x, 1 over e to the x.
Which means e to the minus x gets smaller as time goes on, right? So I want you to imagine that you are driving in Pittsburgh. Apologize for those of you that have to deal with this. You go down our lovely roads. What happens to your car? Boing, 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 right? But if you've got good shocks, what happens to your car? You hit a bump, and then it diminishes over time. Damped vibrations. You close a door, it's got one of those automatic closures on it, so it doesn't slam, right? You push through a door, and it goes. Now, if you've ever had a screen door where that thing broke, and it just flaps back and forth several times, eventually it settles down and stops. Damped harmonic motion. That goes through this all the time. That's the equation for damped harmonic motion. And it shows up, therefore, in differential equations courses, which are applied in physics and chemistry and ecology and all the rest of these places. There is a sneaky way to do this problem, but it involves complex numbers. If you're interested, please come talk to me. My research field is complex numbers. I think they're incredibly cool, but that's a separate game. And then you can actually do this in one step. without integration by parts. But it's way more complicated. Questions? E to the x sine x would be amplified vibrations. So imagine the Gryffindor portrait, Violet the fat lady singing at the glass until it breaks. You put more and more energy in to make that vibration bigger and bigger and bigger. Eventually the glass shatters. If you go down Route 30 and you get to North Versailles, as you go across the Westinghouse Bridge with the steel plant on your left, past the bowling alley, the Westinghouse Bridge has a sign that says brake cadence on the sidewalk. You're not allowed to march in rhythm over the bridge, just in case your marching rhythm emphasizes the vibration of the bridge. The Washington-Tacoma Narrows Bridge shook itself apart because the wind emphasized the vibration of the bridge. It's called Galloping Gertie. It's a great video. It's online. Okay. Questions? Just like yesterday, I skipped something. Everything we've done so far has had something in common. I haven't done definite integrals yet. Now I will again say, I rigged this sucker. I did it on purpose. And this is where having the trig formula sheet is very helpful. What's the antiderivative or the derivative involving cosecant squared? I know I want the antiderivative of that part. U should be the x, and that means that dv should be cosecant squared of x, dx. And that's why I know I want the antiderivative of cosecant squared, which means I need to go to my trig formulas and say, okay, wait a minute, what's the derivative that's equal to something with cosecant squared? So either at the end of chapter 4, page 352-ish, or in the chapter on trig derivatives, which was chapter 3, section 3-ish, I think it was section 3. Why you should have a book. What do we got?
One plus cosine squared x, I break it down now.
That's the Pythagorean identity that involves cosecant squared. Cosecant squared equals 1 plus cotangent squared. We get that if we take the sine squared plus cosine squared equals 1 and divide by cosine squared. By sine squared. But that's not actually going to help me in this case. But remember Pythagoras, we'll need him tomorrow. This is just a derivative. The derivative of some trig function. That's cosecant squared. The derivative of cotangent is minus cosecant squared. So that's exactly the right place to be to do this. Here's that list from page 352. I don't see cosecant squared. If I flip back to chapter 3, where the trig derivatives are, chain rule, here we are. The derivative of cotangent is minus cosecant squared. I don't have the minus sign, so I better put it on the other side. And now I can apply lag time. Sorry about that. And now I can apply my formula. But what do I do with the definite integral part? The fact that there are numbers on here means I should finish with a number. But when you do an antiderivative, we use the fundamental theorem of calculus. You take the antiderivative, you plug in the numbers, right? So I do uv minus the integral v du. But the left part of that is already antiderivatives, isn't it? This bit, I've already done the antiderivatives. So that is now evaluated. This is still an integral, which means it still has the same numbers at the bottom and the top. Minus a minus is a plus. So I'm going to turn this into a plus. So I have x cotangent x with a minus sign, pi over 4, pi over 2, plus the integral from pi over 4 to pi over 2 of cotangent. Cotangent? Wait a minute. We did tangent yesterday. What did we do yesterday for tangent? So I'm going to write this as cosine over sine. And that's a U substitution problem. Oh, good. The derivative of sine, that's on the bottom, is cosine. So I can write this as 1 over sine x cosine x dx. Now here's where I get to say I'm going to be pedantic again. I've already used U. I don't want to use it again. So let's not do a U substitution. Let's do a W substitution. I don't care what letter you use. You want to use U again, use U again. But I'm going to do a substitution here. 1 over sine is 1 over U, and then the du will be the cosine of x, and I'll change the numbers. Now I said I didn't want to do it, so I'm going to use W. And I change my numbers. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 2 is 1. So this integral now has different numbers on it. You don't have to do that. You can leave it in X and go back at the end, right? I did say you could do that. But now I can plug it. I can do that antiderivative and plug in all my numbers. That's going to give me ln of the absolute value of W. Oop, write the numbers in the right order. That helps. And now I just have to plug in. What's ln of 1? 0. And ln of the square root of 2 over 2 is some ugly ass decimal. I'll leave it like that. Cotangent of pi over 2. Cotangent is cosine over sine. What's cosine of pi over 2? Amy's going to yell at you for not remembering the trig table. Cosine is 0. That means that cotangent of pi over 2 is 0. Pi over 4. Cosine of pi over 4? And sine of pi over 4 is also root 2 over 2. And that makes cotangent of pi over 4. So plugging these numbers is actually relatively straightforward. And this is like 1.13 if you plug it into your calculator and get a decimal. But notice I had to use 2 different sets of tricks to do this problem. I had to use the new integration by parts formula, and I had to use a substitution like we did yesterday. We're going to see this frequently where our tricks build on each other. I will see you all tomorrow, early in the morning, and we will do another new formula. Have a wonderful rest of your day, everybody. Don't melt.